So, welcome all. I'm opening the second session of the first day of our great meeting, but I'd like to start by saying a big, huge, large thank you to the organizing committee on behalf of Professor Özçelik, of course, for their courage and their labor to organize such a big meeting in these challenging days. They proved us that there is no such a place to be called far away. And I'd like to inform our speakers that I'm planning to give 12 to 13 minutes to each for them to present their great work. And then I will try to inform them when their times are getting shorter at the last 2 minutes of their scheduled times. So I'd like to invite Dr. Statasko, but I'm also informed that because that he couldn't be able to attend the meeting, Dr. Neslihan Akçay is going to present his talk entitled Incoherence Photospectrometry of Soda-Lime Glasses Substrates. So I'd like to leave our screens to Neslihan Akçay for her to make the presentation.
Okay. Hello, everybody. Thank you so much, Professor Varlıklı. I will share my presentation. So I think you can hear me. There is no any problem with my audio.
Maybe you may want to make the full screen as well.
Okay. Okay. So thank you very much for the nice introduction, Professor. So I'm going to make a talk on incoherent spectrophotometry of soda-lime glass substrates. So this work is a joint work between Belarus and Turkey. Actually, the experiments were conducted in Belarus by Professor Staskov. So first, I would like to mention about my talk. I will start with the motivation of our work at first, and then I will mention about some general concepts in spectroscopic ellipsometry and spectrophotometry methods. And I will mention about the experiment. Then I will try to introduce the electrodynamics models and spectral research areas in our study and basic formulas. Then I will show you our results in this study. So the soda-lime glass, which is commonly known as float glass, is used in a wide variable of applications. In particular in thin film depositions and in the field of thin film solar cells. Actually, the name float glass is coming from the production processes of this type of glasses. So in the production process, molten glass floats molten glass floats on the top of the liquid tin for several minutes while it cools from an initial temperature of approximately 1100 Celsius of degree to 600 Celsius of degree before being removed from the tin bed. That's why this kind of substrate, this kind of glass actually, has two optically distinct surfaces. One side is air side and the other side is tin side. sorry. It has two optically distinct surfaces. In the thin film solar cells research, sometimes the solar cell devices is fabricated in the form substrate form, and the others one is fabricated in the form of superstrate form. So and also in the thin film solar cells research, sometimes different kind of thin films is deposited on the these substrates, and when you make the optical measurements, optical analysis of these films, you should consider the optical properties of the soda lime glass substrates. That's very important to understand the optical properties of the thin films and the thin film solar cells, which is fabricated in this formation. So that's why we aimed to investigate the optical properties of soda lime glass substrates for both surfaces. And also another motivation of our work in the literature, usually the optical constants and refractive index N and extinction coefficient K is calculated by using measured transmittance and reflectance data at the normal incidence of light in the spectral range from lambda is equal to 310 nanometer to 3700 nanometer. But when you came the spectral region, which is lambda is smaller than 310 nanometer, due to the large extinction coefficient, transmittance goes to 0. That's why this method does not allow to us to determine the optical constants N and K in this spectral region. So we that's why we aimed to investigate the optical properties of the soda lime glass substrates by using two different methods in this study. At first, I would like to mention about general concepts in our study. Psi and delta is the ellipsometric angles, which is measured by spectroscopic ellipsometry. And then according to these parameters, one can obtain optical constants N and K, and also dielectric constant. Both the real and imaginary part of the dielectric constant can be calculated by using the ellipsometric angles psi and delta, and also the thickness of the glass, the thickness of the sample at the angle of incidence theta can be also calculated, and EEG energy band gap is also calculated by spectroscopic ellipsometry method. And here other parameters are S, TS, RP, TP are the reflectivity and transmittance in S and P polarized light, and lambda G corresponds to red absorption band order, and omega is cyclic frequency. So here I would like to mention about the experiment and the calculation. As I said before, in our study, we used two different methods, spectroscopic ellipsometry and spectrophotometer, to obtain the optical properties of the sample. So in the SE analysis, psi and delta ellipsometric parameters were measured in the region from 206 nanometer to 900 nanometer at the incidence angles from 55 degree to 58 degree. And in the second method, spectrophotometer method, RS, TS, RP, and TP parameters were measured in the region of region from 250 nanometer to 900 nanometer at two incidence angles theta is equal to 10 degree and 55 degree. And also the calculations was made in 3 different regions. In the spectral range from 260 nanometer to 250 nanometer, as we used SE method, and from 250 nanometer and to 310 nanometer, we used both SE and RT methods. RT corresponds to spectrophotometry method here. I would like to state that again. And in the 3 region, in the spectral range from 310 nanometer to 900 nanometer, we used RT method. And also the dielectric constant of glass is interpolated by the classical dispersion model. So in this slide, I would like to introduce you electrodynamic models and the spectral research areas. So in the first model, you see, we deal with the region which is lambda is smaller than lambda g. I would like to say that again, lambda g corresponds to red absorption. Here, lambda g corresponds to red absorption band order, which is equal to 310 nanometer in our study, because as it is well known, below this wavelength, the glasses has no transmittance in this region. So in the first model, compared to reflectivity, transmittance is practically equals to 0. So that's why we used instead of electrodynamical model of a plane parallel layer surrounded by air. We used another model which is air unlimited medium in this part. And also, for such a simple model, the formulas of analytical calculation of spectra N and K are known by measured at two incidence angles RS in S-polarized light, and also it can be measured by at one incidence angle RP and RS in S and P polarized light. And another way is the measurement of ellipsometric angles delta and psi at one incidence angle. And in the second model, as you see, we deal with the region which lambda is bigger than lambda g. In this region, for the glasses, we can assume that reflectance and transmittance is not equal to 0.
Last 2 minutes.
Sorry?
Last 2 minutes, Dr. Akçay.
Oh my God. Okay, then I will continue fast. So here you see the basic formulas which we used in this study. For the investigation of the optical properties of the samples, the determination of N, K, and alpha absorption coefficient is very important. And here you see an expression is related with absorption coefficient. It includes K extinction coefficient inside. One can use different formulas for calculation of the absorption coefficient. In our model, if you look at the second model, you will see by considering the general conservation law, R plus T plus absorption is equal to 1, as you know. By considering this general conservation law, we can obtain alpha, the expression for the alpha absorption coefficient like that. And in our study, we used a classical dispersion formula by using delta psi 2 SE Horiba software. So let's look at our results. Here you see spectral characteristics of soda lime glass and also clear soda lime glass. We obtained these results from the study of Rubin and et al. They calculated, they tabulated N and K values for clear soda lime glass substrate. And what is the meaning of clear soda lime glass? It's this kind of glasses don't contain no additives other than those meant to affect the manufacturing processing. So we compared our results with this kind of soda lime glass substrate. Here you see 3 corresponds to clear soda lime glass substrates, and as you see the figure inside, the soda lime glass substrates in our studies has strong absorption and calculated and measured values overlaps very well for our substrate. So here you see the optical characteristics of SLC and SLG by using 2 different methods, spectrophotometer and ellipsometric analysis. N was calculated according to psi and delta measured at theta is equal to 55 degree in the region of strong absorption from 206 nanometer to 300 nanometer. As you see in the figure, curves 1 and 2 partially overlaps, and the maximum difference in refractive index sorry I'm sorry. The maximum difference in refractive index for lambda is equal to 364 nanometer is equal to 1.59%. And if you look at the K, the graph of K extinction coefficient, we investigated K values into 3 different regions. As you see, the first region, psi and delta, was used for the calculation. And in the second region, we also used RS and RP at the incidence of angle 10 degree for a model air unlimited glass. And in the third region, we calculated K, the spectra by using the spectra RSTS and the formula which is given in this slide. As you see, this formula was derived by the Rubin and et al. Here you see a table which includes the.
Very sorry, Dr. Akçay, I'm really sorry to interrupt, but you need to wrap it up because.
Okay. So it's about to finish. Just 2 minutes, please. So here you see the ellipsometric parameters psi and delta, which was obtained by SE analysis. We calculated Brewster angle according to the Brewster law. And as you know, the Brewster angle is the angle of the incidence where delta is equal to 90 degree. You can easily see here in the graph. And also you can calculate and refractive index by using a Brewster angle in the SE analysis. So we calculated N as 1.54 and the Brewster angle is equal to 59 degree in our study. So here you see the dielectric constant graph according to the classical dispersion formula. We used this expression for calculation the dielectric constant epsilon, and also here you see the parameters of the interpolation function. So now I will mention about our results shortly. The edge of the absorption bands of SLG glass falls at a wavelength of 310 nanometer, which is equal to 4 electron volt. In the transparency region of this glass, to determine the spectra of refractive indices and absorption, it's sufficient to measure the spectra RS1 angle of incidence less than the Brewster angle. And from the minima on the spectra, RP and psi, or from the change in delta by P, one can determine the Brewster angle and find the value of refractive index at the wavelength corresponding to minimum. So the real part of the dielectric constant of glass in the UV and visible spectral range interpolated by classical dispersion model. Thank you very much for your attention. I'm sorry.
It's okay. We have exceeded our time for 5 minutes, but I think we can tolerate with your second talk. I hope.
Okay for me.
So in the first talk that you have presented instead of Dr. Stasko, you showed us the theoretical and the experimental optical data were well matched with the soda lime glasses. So as I have said a few seconds ago, I'd like to again leave our screens to Dr. Akçay from Başkent University in order her to give us talk entitled Structural and Optical Characterization of Copper tin sulfide tin films prepared by sulfurization of sputtered copper tin copper stack layers.
So now I will start to my second talk, I think.
Yes, please. And again, I will inform you at the last 2 minutes.
Okay. I think this will be short. So. Okay, so sorry. So this work is was done by Belarus and Turkey. You see the research group, Professor Valery Gremenok from Belarus and Dr. Korosko and Dr. Piatlitsky from Belarus and Integral Company. I will talk on the structural and optical characterization of CTS thin films prepared by sulfurization of sputtered copper tin and copper stack layers. At first, I will mention about the deposition process of precursor films and sulfurization process and the characterization of the films. So as you know, the solar cells are classified into three main groups. The first generation of solar cells, second generation, and the third generation. The first generation of solar cells includes the crystalline silicon solar cells, which has a big market share. Actually, it has the biggest market share, over 90%, and its record efficiency value is about 26.7%, which is very close to the theoretical value of the crystalline silicon solar cells. And the second generation includes CIGS, cadmium telluride, and amorphous silicon solar cells, and the maximum efficiency value is equal to 23.4%, which is very close to the record efficiency value of silicon crystalline based solar cells. But first generation solar cells is high cost solar cells because of the production processes of poor silicon and also it's about the material costs, because the thickness of the absorber layer is about 100 micrometer. For thin film solar cells, the thickness is about, actually it's below the 5 micrometer. And they has advantage due to the use of less material, and also it provides the opportunity of flexible substrates. So when we look at leading thin film solar cell technologies, CZTS is very similar to the commercial CIGS and cadmium telluride solar cells, but CIGS and cadmium telluride has some toxic elements like cadmium, and there's a problem with the scarcity of indium and gallium and tellurium and selenium, and also high cost of indium is also another problem, because casterite materials, CZTAs materials, is very similar to CIGS. It's very popular among the inorganic material, inorganic absorber materials, because it includes earth abundant, environmentally friendly element and low cost, and its band gap is equal to 1.5 electron volt, and it has a high absorption coefficient, which is bigger than 10 to 5 centimeter minus 1, and so here you see the maximum efficiency value is about 12.6%. And but there are some problems with the casterite materials, like a VOC deficit. So the low VOC, the reason for VOC deficit is explained by deep defects and secondary phases, binary and ternary secondary phases, which includes inside the material, and because of the compositional problems. So that's why the researchers still look for new absorber materials for thin film solar cells. CTS is an alternative material to CZTS. So its band gap is change from 0.8 to 1.8 electron volt. It has also p-type conductivity and a high absorption coefficient, and its theoretical efficiency is about 30%. But it has a polymorphic structure. It can be formed in cubic, tetragonal, triclinic, and monoclinic structures. Monoclinic is the best, is the most stable phase among these phases. It's a perfectly ordered phase. So here you see the maximum efficiency values of CTS-based solar cells. It's about 6.7%. Which was fabricated by co-sputtering technique. So the CTS films can be produced by different approaches, vacuum-based and non-vacuum-based approach. Although the non-vacuum-based approach is preferred by the researchers mostly, the maximum efficiency was obtained by vacuum-based approach. As I said before. So you can produce the CTS films with two different process. One is one-step process, the other one is two-step process. In the one-step process, it includes simultaneous deposition of copper, zinc, tin, and sulfur components at high temperatures under H2S gas. In the second, in the two-step process, at first the precursor films are deposited at low temperatures, and in the second step, the precursor films are thermally annealed at high temperatures. So in our study, we used sputtering, DC magnetron sputtering method to produce precursor films. As you see, we used co-sputtering technique, and we formed the sequential stacked deposition. Here you see copper, tin, and copper, and here you see the deposition parameters, and the thickness was about 600 nanometer. That's not right, I'm sorry. So in the sulfurization process, you see the process was conducted under N2 and S2 gas atmosphere. and the working pressure is equal to 0.6 millibar, and the sulfurization temperature is equal to 550 Celsius of degree. And we make the sulfurization at different time. At different times from 30 to 180 minutes. So we cannot obtain, we cannot make exact structural analysis of CTS films by XRD analyzers, because for different phases and the peaks overlaps, so it's very difficult to obtain the exact results by using only XRD analysis. We used a grazing incident X-ray diffraction of CTS films for the structural analysis. As you see, we obtained a monoclinic phase with 2-1-1 preferred orientation. Here you see the purple color corresponds to CTS phases, and the main peak was obtained at 28.5 degree. So as you see in the graph, the intensity of 2-1-1 main peak is increasing to 120 minutes. And also in the XRD pattern, we obtained copper sulfide and tin sulfide secondary phases. From 30 minutes to 90 minutes, sulfur are dominant for our samples, and at 150 minutes and 180 minutes, CTS phase is the prevalent one in our results. So we also calculated some some structural parameters by using XRD results. Here you see the lattice constants ABC beta and interplanar spacing, grain size, dislocation density, and lattice strain, and so on. As you see in this table, A, B, and C lattice parameters are increasing with increasing the annealing time, and beta is decreasing by increasing the annealing time. So as a result of unit cells widening because of the reaction between metals and sulfur, and also dislocation density and microstrain is decreasing. This indicates the structure of the film is improving. So that's the Raman spectroscopy analysis. We obtained a tetragonal phase in Raman spectroscopy analysis, and also the main peaks of CTS phase, and also copper sulfur secondary phase. And you see a EDX and SEM analysis of the films. And at first, I would like to say the copper tin ratio is under 2 for 60, 90 to 120 and 150 minutes, but it's over 2 for 30 minutes.
You have exceeded your time, Dr. Akçay.
Okay, it's about to finish. These are the optical properties of the films, and we calculated the absorption coefficient of the films, and R is the reflectivity of the sample annealed at 60 minutes is the highest due to the rather smooth surface, which is consistent with the SEM analysis. And also here you see the band gap values, which was calculated by using tau correlation, and the results are very consistent with the literature. So that's all. Thank you.
So we thank you. I think that you did a very good job actually by presenting two different titles, one after another.
Yeah,
And I'm quite sure you got a little bit tired. As far as I can see, there is no questions at the chat board, but in short, you have actually shown us that the process conditions are very much effective on the material properties that you will gain, right?
yeah, thank you so much. Thank you.
Okay, so thank you, Dr. Akçay, once again, and I'd like to invite Dr. Kurt from Istanbul Medipol University for him to give us his speech on the plasmonic light management in PBDBT-ITICM inverted organic photovoltaics.
Okay, hello everyone. It was a nice talk, Neslihan Hanım, and I'm going to start just a second. I have to get rid of this one. Okay, perfect. So the work is technically supported by TÜBİTAK, and we actually try to use plasmonic nanoparticles and nanoparticle arrays to actually manage the light within a solar cell. It was an extension of my thesis work previously. So the outline is going to be simply what is light management in thin film organic photovoltaics, and how can we actually produce pseudo arrays of gold nanoparticles for plasmonic enhancement, field enhancement. And we are going to see some finite difference time domain simulations for spectral response of these arrays. And we are also going to see experimental deposition and growth procedures. Then we are going to implement these nanoparticle arrays in inverted photovoltaics. One of the examples is going to be PBDTBT based OPVs. And then I'm going to show you preliminary results of experimental enhancement in solar cell efficiency. And I'm going to talk about future work, and we are going to be done. So light management in OPVs is actually originates from the really limited thickness of their limited thickness. They have to be below 200 nanometers. If you make them larger, you are going to lose efficiency. This actually originates from the low absorption coefficients for some of the donor polymers, and low dielectric constant, which actually induce charge separation problem. So not all absorbed photons actually produce excitants, and they cannot be separated sometimes. And they also have low mobility. These are the most important parts, and small excitant diffusion lengths, and these limit their thickness below 200 nanometers. So in order to remedy that, in 2010, Harriet Rotter and Albert Pohlmann was presented some possible solutions to these problems using plasmonics. And plasmonics is technically collective oscillations of electrons in the vicinity of a metal dielectric interface, and they can actually enhance the incoming photons, and they can actually condense them in close proximity at that interface. And this increased field efficiency can actually be used to actually improve the efficiency of solar cells. So there are a couple of ways. You can couple them at the back electrode, like a silver electrode, for example, at the back contact, or you can put some at the top, so you can scatter, and the light is going to spend more time inside the thin film, so it's going to be more chance to actually get absorbed. Or you can directly implant them inside a bulk heterojunction, for example, and they can actually produce some increased efficiency through field enhancements. So in this work, we are actually directly aiming for this absorption coefficient, so we can actually get more light inside to the system. So in order to make this, we need some plasmonic nanostructures, and in order to effectively produce them in large scale and deposit them with an ordered manner, we use reverse diblock coupling micelle lithography. And it actually uses a block copolymer consists of a polystyrene part, a polystyrene block, and P2VP vinyl pyridine block, two vinyl pyridine block. And one of them is more apolar than the other one. So when in a toluene solvent, they are going to form mine cells, and we can actually load these mine cells using metal salts like hydrochloroauric acid, and then we can actually use reducing agents, or oxygen plasma can actually reduce them as well, and we can actually have gold nanoparticles, and they can be easily applied to the surface through spin coating, and they are going to produce you somewhat pseudo arrays. They are going to be well defined in terms of diameter. For example, this is one of the earlier works of our group. So in this one, they have a radius around 8 nanometers, and they still show up to a third nearest neighbor relation. So, and they can be applied to many of the surfaces, like you can also apply them to ITO. And if we actually take the simulations and check what's happening at that interface, for example, these are on glass, for example, and this is S and P polarization, and I combined them, both of them. So technically, it actually enhances the incoming electric field like up to 15 times. So it's quite actually effective for producing some excitants in the vicinity of these nanoparticles, so you can actually collect them easier, especially if they're close to the cathode and anode, depending on your structure. In inverted device, it's going to be the cathode. And they have an absorption around 550 nanometers since they are gold, technically. And what if we actually play with the array parameters, like the distance between the particles and the particle size? As we increase them, they are going to actually, of course, they are going to have a better field enhancement, but still they are going to reflect some of it through scattering. So there should be an optimum particle size when you actually put them inside an OPV. So in order to get this problem, we actually used, for example, we simulate them on ITO on sol-gel zinc oxide, and see what's happening with different parameters, with different nanoparticle radiuses and distance, interparticle distances. And what we see is, for example, if I'm going to compare, for example, this is this one is just without any nanoparticle. I should have this one. Sorry. Okay. Without nanoparticle, and these are 10 nanometer nanoparticles, and these are 25 nanometer reduced particles. So as you can see, when the light actually gets inside, especially if they are large, they are going to reflect most of it, and very little light is going to get inside the bulk heterojunction, as you can see from here. But of course, they are going to enhance the field in their close vicinity. So these are still going to be applicable. But as you can see, if you increase the size of the nanoparticle, simply they are going to reflect more, and most of the light is not going to get inside the bulk heterojunction. So in order to, so we should have somewhat optimum particle size, so we can actually effectively use them to increase the efficiency of solar cells. So we applied them on sol-gel zinc oxide thin films, since sol-gel zinc oxide is commonly used for electron transport layers. And this way, the gold nanoparticles are going to be directly in contact with the bulk heterojunction. So in order to do that, we use a common method with starting with a zinc acetate and monoethanolamine, and we hydrolyze that, and you can easily spin coat on surfaces with a controlled thicknesses easily, and you just heat treat them at 200 Celsius degrees for an hour, and you are going to have a sol-gel structure. And we used the copolymer lithographies that we use, and after an oxygen plasma step, we easily obtain these structures on zinc oxide thin films. And in order to grow them, we used a couple of methods. The first method we used didn't actually work effectively. So we started with, we actually cut the plasma treatment time with half, and we applied slight, let's say a mild reducing agent and gold precursor with certain concentrations. But when we actually try to grow them with different times, we actually get more nucleation than growth. So we actually have, we obtain actually extra nanoparticles, which we don't like. And we again clean up the rest of the polymers, so we can actually still have them to use. But this route was not effective, and as you can see, it actually creates new nucleation sites and they produce new nanoparticles, which are not, they're actually disturbing the pseudo array anyways. So we use a milder version. We completely burn out the micelles with oxygen plasma. Then we completely clean them to actually get rid of any possible nucleation sites for other growths. So then we use extremely mild, which is extremely mild reducing agent, L-ascorbic acid. It's vitamin C technically, and CTAP for reducing the growth for an effectively. And we use less gold precursor. And in this case, it took a few hours, but we can actually effectively grow them to up to a 25 nanometer size. And then we actually try to implement them inside a inverted organic photovoltaic device. And in this case, we use PDBT ITCM. It is one of the new kind of polymers, which gives you quite high efficiency, up to like 10 to 11, sometimes 12% efficiency. And since it doesn't have any fluorine, it has a better degradation mechanism, so it's not going to decay that fast. And we use 1-to-1 ratio and with a high concentration in chlorobenzene and dioido-octane solvent. And we also get their optical properties from variable angle ellipsometry, so we can actually simulate them as well. And we also extracted all the necessary information for the ITO zinc oxide, silver molybdenum oxide to actually complete simulate the device. And then we actually simulate the device using numerical finite difference time domain simulations. And we try to actually extract the external quantum efficiency as well and the short circuit current. And short circuit current actually shows us two minimal maxima at 10 nanometer and 15 nanometer. And
Last
as you can see,
2 minutes.
okay. And afterwards, we said these are possibly the most effective sizes that we can actually implement in this kind of device. So we implement them directly with certain sizes, and we actually get quite decent efficiency and average efficiency of 8.77 with 16 nanometer gold nanoparticles. But as you can see, 12 nanometers is lower than the 7 nanometers. So there is going to be a somewhat polishing and more experimental work is needed. And the best, most highest efficiency that we get from one of these devices are 9.5, which is quite decent. And in the future work, we are going to actually continue with the external quantum efficiency measurements of these structures. And we are also going to check transient photovoltage measurements and impedance spectroscopy for steady state. So we can actually get how much charge carrier density that we can actually produce inside the device. And we are also going to check if these extra charge carriers is actually affecting the electroluminescence of the device. Are we actually extracting whatever, extracting the charge carrier that we produce through plasmonic enhancement? So we are going to also check electroluminescence for this. So thank you for your attention. If you have any questions, I would like to answer them.
Thank you very much, Dr. Kut. It's a very interesting speech, and thank you for sharing your unpublished results with us as well. I'd like to remind the audience that they can ask their questions through the chat board once again, but Dr. Kut has showed us the importance of interface engineering on getting high efficiencies in solar cell applications. I've got the question while waiting for the audience if they
Yeah, of
will
course.
ask one. In your route 2, you're applying oxygen plasma right after the coating of the nanoparticles, let's say.
Yes.
Did you plan or did you check the effect of the time that you apply oxygen plasma or the power of the oxygen plasma that you apply on the properties of the nanoparticles that you would obtain?
For gold, it was in 2016. We actually did that in my thesis work. So technically, the oxygen plasma that we use is like 30 watts. So and the pressure was around like a torr. So technically, it was a chemical oxygen plasma. It wasn't a physical one. So it only reacts with the polymer structures and it only reduces the precursor. So we actually tried with different plasma times, and we didn't have any problems for the gold. We had some problems with, for example, different nanoparticles like lithium fluoride.
Thank you.
Thank you.
For this satisfactory answer as well. So if there is no more questions, I'd like to proceed with our next speaker. And I'd like to ask Meltem Hoca to present the video recording, because I'm informed that although Giovanni Pica is with us now, he also has sent a video recording. We will listen his talk on accelerated thermal aging effects on carbon-based perovskite solar cells, point experimental and theoretical analysis. And Dr. Pica is joining us from Italy, from University of Pavia. Please.
Thank you. I will share my screen. Okay. Can you see my screen?
Yes.
Perfect. Okay. Good morning to everyone. Thank you for this opportunity. I'm very glad to be here. And today I will present you my work that is entitled Accelerated Thermal Aging Effects on Carbon-Based Perovskite Solar Cell. And this is a joint experimental and theoretical analysis. In the field of modern photovoltaics, hybrid perovskite solar cells have far outstripped most of the current technology, with their power conversion efficiency reaching 25% and beyond. These kind of cells are characterized by high efficiency, low cost, but the stability is one of the last open issue on this technology. Here you can see an image of this kind of cell, of the cell made with this technology, in which the active material is the perovskite that has a typical structure of ABX3, where A is the organic cation, B is the inorganic element, and this is why they are called hybrid perovskite solar cell, and X is the halide element. In this work, I used the triple junction carbon-based solar cell that are represented here. They are well known for being a long-term stable and cheap solution that can be what the market needs. This is particularly true at temperature above 70%. Indeed, thermal stress as a reason of degradation is often underestimated. And in this work, we address this issue by monitoring the effect of thermal aging by imposing a prolonged temperature cycling stress with two different temperatures, in which these temperatures are 50 degrees and 80 degrees, and the temperature with a relative humidity of 72%. The temperatures chosen are respectively below and above the phase transition temperature of the active material, that is around 54 degrees. And we measured these cells under a very well-defined aging protocol consisting of two different periods of time. In the first period, we have a situation of low humidity and low temperature, indicated with the blue slots in the figure, and a situation of high humidity and high temperature, indicated by the red slots. In the dark red are indicated the slots in which we increased the temperature to 80 degrees. So this is the protocol, and these are the results. And in the left-hand image, you can see the behavior of the PCE, the power conversion efficiency, through the entire cycle. And at first glance, you can see that the PCE has a decrease from an average value of 13.5% to an average value of 10.6%. But at closer inspection, you can see that there are two different regimes. In the first half of the cycle, here, where the temperature was set to 50 degrees, the PCE is quite stable. While switching to 80 degrees, the PCE has a drop of around the 20% of the initial value. This is for the stressed cell. For the reference cell, instead, you can see that the PCE is quite stable throughout all the entire cycle. In the right-hand image, instead, you can see the current voltage characteristic for particular times, which shows to record these, obviously, through the entire cycle, but here are shown the ones corresponding to the initial, to the start of the cycle at time 0, in the middle of the cycle, and at the end of the cycle. And as you can see in the table here in the inset, the VOC decrease in a way that it is uniform through the entire cycle, while the fill factor has a decrease, but it is quite stable for the first half of the cycle and then has a drop. And this resembles the behavior of the PC that was stable and then has a drop. So at the moment, we have information about the open circuit voltage, the short circuit current density, the fill factor, and efficiency. And these are parameters that can be very useful to check if a degradation occurs. But they don't say nothing about what is happening inside the device. And the solution is to model the device as a circuit with load and resistances, the so-called single diode model that is represented in the figure. And then we have to fit the experimental data with this function that describes the behavior of the device, and then we can extrapolate the parameters of the model. This is the formula that we use for the fitting, that is derived from the Shockley equation. And the parameters that we want to extrapolate is the reverse current here, the ideality factor, the series resistance, and the shunt resistance. Here, there is a representation of the fitting procedure that we developed. We decided to use this function, and we have to find the zero of this function, and we use the bisection method. And then, by using the experimental data, some initial guesses of the parameters, and the variation range of the parameters, we can perform the fit with the last squares method, and then we can obtain the fitted parameters. Here, you can see the JV curves with the experimental data and the fitted curve at the same times of the slide before, at the beginning, in the middle, and at the end of the cycle. And you can see that the experimental data are well represented by the fitted curve for all the cycle. Then we decided to use this fitting procedure to understand the behavior of these parameters through the entire cycle. And as you can see, the ideality factor varies between 1.7 and 2.3, and this is in agreement with other works. The saturation current is the parameter that varies the most, between 10 to the minus 11 to 10 to the minus 7. And this is due to the strong sensitivity of the saturation current on the recombination processes. The shunt resistance is quite stable for the first half of the cycle, and then it has a drop as the PCE, and the series resistance is barely affected by the stress. So the results are constant series resistance and decrease in the shunt resistance. And this suggests a minor effect of the aging on the bulk of our devices, while indicates a severe impact on the device interfaces. We want to study more in depth these phenomena, and we performed morphological and structural characterization. Here in the inset, you can see the SEM of our device in cross section for the reference cell and the stress cell, and you can see that there are no strong deviations, so the cross section are very similar. From a structural point of view, you can see the absence of the PbI2 peak that arose at 12.4, and this is another addition to say that the composition of the bulk has had no variation. At the end, we did also optical characterization. So we measured the PL signal at the beginning and at the end of the cycle for the reference cell and the stress cell. And as you can see, for the reference cell, there is is not so much the decrease in the PL signal, while there is a more severe quenching of the PL signal for the stress cell of around the 70% of the initial value. In this case, we are interrogating the interfaces more than the bulk due to the penetration depth of the light that we used, because we used a 460 nanometer laser light that, according to the Lambert-Beer equation, has a penetration depth of few hundred nanometer. Our active material is infiltrated into a scaffold of 500 nanometers. So this is why we claim that we are interrogating more the interfaces. So according to this characterization, we can say that degradation occurs at interfaces, and this is in line with the previous characterization, the morphological and structural characterization, with our fitting procedure that we developed, and with the experimental data of the decrease of the PC. And this is all from my side. I want to thank you, my group, the PB²2 group from Pavia, and in particular Professor Giulia Grancini. And here you can see our website if you are interested in knowing more us. Thank you.
Thank you very much, Dr. Pika. This very condensed and good talk. So you also addressed the importance of the interface engineering.
Yes.
Because as a chemist, if I'm wrong, please correct me. As a chemist, you check the properties of the material first, yeah, the bulk material, and see no difference. So
exactly. Yeah. The material instead in the bulk is the same substantially. And so the decrease of the PC has the only reason in the interfaces between all the stack that we built.
Okay, thank you very much again. And as far as I can see, we do not have any questions. So I'd like to shift to our next speaker, who is Sumaya Klovic from Graz University of Technology, Austria. And we will enjoy the talk entitled Revealing the Photo-Triggered Structural Dynamics of Photoresponsive MOFs Grown on Oriented Ceramic Thin Films. The screen is yours.
Thank you very much for this kind introduction, and also for giving me the opportunity to join the second International Conference on Light and Light-Based Technologies, and also for giving me the possibility to present my work, which is dedicated to reveal the photo-triggered structural dynamics of photoresponsive metal organic frameworks oriented in ceramic thin films. So I'm part of the small angle X-ray scattering group, which is located at the TU Graz outstation at the Elettrosincotrone in Trieste in Italy, as indicated here, which together with the deep X-ray lithography beamline is one of the two Austrian beamlines there. So my work is based on metal organic frameworks, or short MOFs. And here on the right side, you can see a schematic representation of this class of materials, which basically consists of metal nodes that are connected by linker molecules. And depending on the type of linker molecules that you use, you end up with two-dimensional MOFs, or as depicted here, with three-dimensional pillared metal organic frameworks. Yet I'm interested in thin films, especially in heterotextually grown MOF structures on solid substrates. And in the first part of my talk, I intend to describe the structural design of these films. Our MOF of interest is the flexible DMOF1, a structure that consists of zinc nodes that is connected by terephthalic acid these H2BDC and DAPCO molecules. Why? Because the pores of the DIMOF1 can be infiltrated by a chromophore, which provides, therefore, us desired photoresponsive behavior. And finally, in the last part of my talk, we will see that this structural design gives us photoswitchable MOF films that we can switch reversibly and on demand. But first things first, let me explain shortly the structural design of our films. And for this, I would like to bring a very trivial example. So imagine you make yourself a sandwich and you start with a bread. And you put on the bread layer by layer a piece of cheese and then let's say ham. And the edges of each layer are precisely matching the one from below. And this is basically the idea of our film structure. So we start with a solid substrate, here in gray, and we, on that, deposit copper hydroxide nanobelts. The substrate size can be chosen as required and indicated down here. You can use silicon wafers or soda lime glass. We deposit then copper hydroxide nanobelts, which serve as the fundament for the next layer. And the term nanobelts come from the belt-like shape, which you can see already by the polarized microscope, but much better by SEM. In the next layer, the copper hydroxide nanobelts are converted to the copper BDC MOF. And the triangular shape, as pictured here, can be clearly seen by SEM. We now speak of an heteroepitaxial film or epitaxial film because the crystal lattices of both the nanobelts and the copper BDC are perfectly matching, both if we look here from the left side or from the front side. And to deduce and characterize the orientation of this film, one can perform XRD measurements and to evaluate how the lattice parameters are oriented and to conclude what is shown here, that the axis B is matching the axis A. In plane XRD is a helpful tool here. Now, the copper BDC layer is ready and it serves mainly as a supporting MOF layer or short SIR-MOF. So for the next step, we chose to grow the zinc-based MOF, or in other words, DMOF1, that consists of zinc nodes that are connected with DAPCO, which would be this nitrogen-containing molecule up here, and terephthalic acid. And this DMOF1 was reported to have exceptional flexible properties by Kitagawa and co-workers. However, when we grow DMOF1 in thin films, the structure has a lattice mismatching of 3%, which leads to a rather textured structure. And the exact growth is currently under investigation, and I do not want to go much into detail here. For scattering experiments, as we do them usually, we use a two-dimensional detector, which has the great advantage that by one look, you gain information on, for example, preferential orientation, if some crystallites are on the surface, for example, but you also have information in the out-of-plane direction, which is indicated here with this yellow frame, in the in-plane, which would be the light blue frame. An integration of this two-dimensional pattern, which you do to understand, for example, how your film is oriented, you typically end up in an intensity in reciprocal space or Q space. So if we integrate now in the out-of-plane direction or in the in-plane, you end up with this scattering pattern down here. But let us come back to these structures. We are now, we have grown the DMOF1 structure, and we usually end up with an opaque film as shown here in the picture. So we are now ready to implement the photoresponsive unit, and we do so by infiltrating the chromophore, which usually we use isobenzene here, inside of the MOF pores, which give us usually this yellowish MOF films. And the successful loading we confirmed by infrared measurements, which were then supported by UVs. So now we are at the stage where we are ready to photo switch our photoresponsive MOF films. So I will shortly show you this experimental setup that we typically employ. And this configuration depicted down here shows you a grazing incident small angle X-ray scattering setup, which is typically employed if you work with thin films. So what you do is you probe your structure by synchrotron radiation, and we use X-rays because we want to know and we want to deduce structural information. By selecting the proper angle, indicated here by alpha, the very uppermost layer, so your DMOF1 structure with your chromophore can be probed. So the first pattern will give you information only about the infiltrated DMOF1 structure. Once you turn on the laser pulse, given here in green, to photo switch the structure, we define this time as time 0, given here at this frame. Which means before this time, the non-switch structure is probed. And after time 0, which means when the laser pulse arrives on the film, the scattering signal starts to change due to the photo switching of the structure. This means the combination laser light with synchrotron radiation, in other words, X-rays, gives you directly the information on the structural changes that occur inside of the structure, and we typically track these transiently. But if we take now a closer look on the structure itself, so what happens with the chromophore inside of the MOF cage? In its relaxed stage, when we infiltrate the isobenzene, it's in its trans configuration. So it pushes the entire structure to fit properly, and this is comparable to an extended spring, let's say. So now when we employ UV light, which is what we do to switch the chromophore to its cis configuration, so to its excited stage, the molecule shrinks in size, which means that the entire MOF structure relaxes back. And the structure requires now less space, and this is again comparable to a relaxed spring. And to give you a feeling on the time scale of the photo switching of our structure, so as you can see, we can cycle this. We switch forward by UV light, and we switch back by visible light. We speak that we are in the range of seconds, both for the forward switch and the back switch. So as I already mentioned, the photo switching is a reversible process. And what we observe here when we take a scattering pattern of the structure, which is relaxed, so I call it here in the off state, we can switch it, so we can switch it on the structure by UV light. By UV light, you can switch it on. So what we see is here a splitting in the reflection. And we can switch the structure back in its off state, again by visible light. We can repeat this process, and as you already see, we can cycle this on-off behavior. When we take a closer look on the scattering pattern, just to give you a feeling what it looks like when you watch the switching on the two-dimensional detector, I marked it here with this red circle. So you see this splitting in the reflection given here by these two lines that appear at the end. So you can really track the structural change already on the detector. And as we aim to elucidate the switching dynamics in the films, which will be assessed in the future, a method to do so is called pump probe. And we at the SAX beamline have such a setup, as shown here in the schematic representation, where the laser light is transferred directly to the beamline via this transport line, and it meets the sample positioned here on the online table. And the idea is that the laser pulse pumps ultrafast phenomena, whilst the time-delayed synchrotron radiation probes the transient sample response. As a laser source, we use a femtosecond laser, which operates at UV, vis, and infrared light, and this opens a great field for various systems and applications. And anybody who's more interested into this setup, I would recommend to check out this paper where it's very well described, much in more detail. So let me come to a conclusion. Here we have shown the successful growth of thin MOF films on solid substrates and the flexible behavior of DMOF1 in thin films. Also, we have shown the successful infiltration with the photoresponsive chromophore, which gave us photo-switchable structures, which we can switch on demand and for the first time reversibly as well. I have given you here a small picture where you can see what it looks like when you're in operando. So this would be a MOF film that we are now switching, let's say. And as you might imagine, there are further works going on. So future work will address especially the infiltration process of the chromophore. Also, as I said, to evaluate the structural dynamics, to know how the switching is propagating inside of the film, and moreover, the chromophore switching itself. And last but not least, I would like to thank the SAX group, especially my supervisor, Professor Heinz Aminich, as well as the Falcaro group at the TU Graz, which were especially supporting me regarding MOFs, and all of the wonderful colleagues and collaborators I had the chance to work with so far, and of course also to the funding. Thank you very much for your attention.
Thank you. Thank you very much, Sumaya Klovich, for the nice talk. For the nice talk on photo-switchable metal organic frameworks. I've got a question to ask because as far as I can follow, there is no questions from the audience. You have chosen a diazo structure in order to insert in your framework. As far
Yes.
as I know, those kind of structures are not very stable under irradiation.
Well,
why did you choose that chromophore? And do you have any other options in order to replace the diazo structure?
Well, the structure is a metal organic frameworks, and they themselves are pretty stable. What we have seen so far is that we apply very high repetition rates by the laser. We see some kind of, let's say, ablation of the structures and so on. But what we did not see is that the azobenzene itself is like destroyed, or that it goes out of the pores. So the concept with the MOF and the infiltrated azobenzene inside was shown and proved already with other work of other people to be quite stable, let's say.
How long do you think that your devices in your future will last? The durability, and what's your target of durability? And if you consider that, would you reconsider the stability of diazos?
Well, let's say it would be perfect if it would be stable over weeks, months, even years. For now, I think we are pretty stable, so we are certainly more stable over weeks. But I think there is more to improve to reach, let's say, a stability of months. Yes.
Thank
and
you.
I think to reach that, you could maybe play with the acid compound itself, to put maybe just the design of the film itself needs to be adapted for that. Yes.
Thank you very much for the satisfactory answer as well. And I'd like to invite our next speaker, Aytaç Onur from Erciyes University, Department of Electrical and Electronics Engineering, to give his talk entitled Effects of the Electric Spacer on Absorbance Characteristics of a Dual Band Large H-Shaped Perfect Absorber. The screen is yours.
Thank you.
Will you need any assistance? Okay, great.
Oh, thank you. Yes. My name is Aytaç Onur. I am a PhD student at Department of Electrical and Electronics Engineering at Erciyes University. I will talk about a perfect absorber. This is a plasmonic nano antenna array. We study about perfect absorbers for sensing applications, and I will give you the presentation content. We will talk about perfect absorbers, and we will look a simple study from literature. After that, I will talk about our perfect absorber nano antenna model. We will look the geometrical parameters, spectral responses, and absorption ability of the perfect absorber. We will see electric field distributions and the geometrical parameters. So we can say what's the perfect absorber? This is a new research area of metamaterials. This is a nano antenna array model. and they can support near unity absorbance within a narrow frequency range. Plasmonic perfect absorbers are plasmonic nanoantennas that absorb almost all radiation or light coming from the resonance frequencies, and they operating in the infrared and visible regions to use for biomedical sensing applications or surface enhanced spectroscopy applications. This is an important study at literature. This is a dual band perfect absorber model by Chen. We can see this nanoantenna model have 4 layers: silicium sprat, gold film, magnesium fluoride, and the nanoantenna gold nanoparticle at the top of the structure, and they get 2 resonance frequencies in this study. And the 2 resonance frequencies are nearly unity, we can see, and the near field enhancements are morely greater than 5,000. After this study, they made the experimental work. At these 2 resonance frequencies, they detected 2 different molecules at the same time. So, and this is our perfect absorber model. Firstly, this H, we set large H, or we can say big H, because firstly, this H model is presented by Erdem et al. For a nanoantenna model, and we also we study about this for making a perfect absorber model, but it was only one resonance frequency. The first frequency absorption rate is not enough, so we changed in our study this H model for a big or a large model. We changed the geometrical dimensions, geometrical parameters, and the layer thicknesses of this structure. So we get 2 resonance frequencies, and all the resonance frequencies rates are nearly unity. We can see the geometrical parameters: silicium sprat, gold film, magnesium fluoride, and gold nanoparticle at the top, and the other geometrical parameters of this H model. So we can change the dielectric supras for 3 different layers, and by using magnesium fluoride, silicium dioxide, or aluminum trioxide, we can get also 2 resonance frequencies, and their absorption rates are also nearly unity. We can analyze for all the electric supras the absorption ability of this nanoantenna structure. If we use magnesium fluoride, firstly, at first resonance and the second resonance, absorption rates are nearly unity, and we can get absorption rates at this formula: 98.9 at first and 99.9% at second resonance frequencies. These absorption rates are very important for sensing applications. So these rates must be nearly unity. And the near field enhancements at first and the second resonance frequencies, we get 1,200 times at first, and the second, they are also highly rates. We can change the electric supras. We can use silicium dioxide, and also at first and second resonance frequencies at 97.7 or 99.9 absorption rates in this dielectric supras, and also same as the other work, the electric field enhancements. And the last dielectric supras, aluminum trioxide, we get two also resonance frequencies. The first is 95 and the second 99.6. Also, we can say they are nearly unity. Also, in the study, we can change the geometrical parameters of the non-110 model. If we get nearly unity rates, that means we can use or we can make the structure at these different geometrical parameters. So at the first, we can see we can change the this parameter, the length of the structure. When the L increases, the resonance frequencies are decreases. Also, we can change the unit cells. We can change length of the unit cell. So absorption spectra of the unit cell, we can see at the second part. When the H increases, the geometrical parameters are also increases, and we can change the other geometrical parameters or the period of the structure. This absorption values we can get. Also, we look the effects of the clotting medium of resonance frequencies. The perfect absorber is we use the clotting medium layer for different refractive indices. Also, we can say that the refractive we get nearly unity rays of these materials. So we can say the optical characteristic of the perfect absorber are depends on geometrical parameters. Also, the resonance frequencies of this perfect absorber can be tuned by the changing the geometrical dimensions of the perfect absorber arrays. And also by using clotting medium, we can say it is observed that the spectral response of designed perfect absorber is so sensitive to refractive index variations. And the conclusion, we can say perfect absorber array has a dual band spectral response, and the locations of the resonances can be adjusted by varying the geometrical dimensions. And the perfect absorber array with adjustable spectral responses can be useful for infrared sensing applications, enhanced near field distributions, and dual band spectral response that will allow sensing that we can use in biomedical sensing applications. And the next step, we want to fabrication and characterization of proposed perfect absorber nano-antenna array. And thank you for your attention.
Thank you very much. We do not have any questions yet. Thank you for summarizing your work on the effects of the dielectric spacer on H-shaped absorbers. I've got one basic question. Why do you want to antenna the IR area? What is your motivation behind your interest in the infrared region?
Yes, we are studying on metamaterials and plasmonics, nanoantennas. So in literature, very important works we see for perfect absorbers. And I study or I try some models like this H model, different structure models. I tried and we get good or nearly unity rates are very highly absorption rates. So we are now also working on this perfect absorber arrays for fabrication and characterization.
Okay. Thank you. Thank you. I touch on her once again. Now I'd like to invite our next speaker, Esra Koç, from Top University of Economics and Technology, Electrical and Electronics Engineering. Esra Koç will be our last speaker of this session, and she will present us her talk entitled Optical Systems Design in LED Lighting Luminaires. The screen is yours.
Hello everyone. Can you see my presentation?
Yes, we can.
Hello everyone. Thank you for this organization to Gazi University. First of all, I am Esra Koç. I am a postgraduate student in Top University Electrical and Electronics Department. In addition, I work as an expert engineer in the LED technology department at Özdisan Electronic Company, which is the largest electronic equipment supplier in Turkey. My thesis advisor is my dear teacher Ibrahim Tuna Özgür. Today, I will tell you about the optical system design of the LED lighting fixture we are working on this thesis. The titles I will explain in the content of the presentation: LED light source, optical system design approach, experimental studies, and conclusion. First of all, I want to explain lighting, light and illuminance. Light is the portion of the electromagnetic spectrum to which our eyes are visually sensitive to. Illuminance is equal to the number of lumens falling on each square foot of a surface. There are the types of lamp in our lives since 1800s. In this presentation, we will handle the LED light source with the most advanced technology. First of all, I want the origins of LEDs. Electroluminescence discovered in 1907, first LED created in 1927, first practical use LED created in 1962. In daily life, we can come across LEDs in TVs, telephone lamps, home lighting, and all kinds of electronic equipment you can think of. Although LEDs are a relatively old technology, they have witnessed a dramatic leap in the 1990s due to new semiconductor materials developed in the search for red, green, and blue lasers, packaging innovations, improved heat sinking and advanced reflector designs, advance in wafer bonding, and transparent substrates for improved light extraction. And how does an LED work? LEDs are semiconductor diodes that permit the current to flow in only one direction. The semiconductor material is layered as an p-n junction. When a suitable voltage is applied to the leads, electrons are able to recombine with electron holes within the device, releasing energy in the form of photons, hence the name light emitting diode or LED. Different materials produce light with different wavelengths and thus different colors. We will more detail. The N material has an excess of electrons, whereas the P material has electrons missing electron holes. Applying a voltage across the PN junction moves electrons toward the junction of the two materials. Electrons from the N material fall into the holes of the P material. In doing so, the electron moves from the high energy level to lower one, and the energy difference is emitted as light or heat. And advantage and disadvantage, we can see advanced LEDs high efficiency, increased reliability, more quickly, easily be dimmed, and since more of the energy drawn is converted into visible light, less is the convert into wasteful heat. And silent operation is important. Wide range color temperatures, excellent color rendering, CRI, and don't contain mercury. We can say disadvantage, higher initial costs, thermal management, color maintenance, and heavy compared to old lamps. Design is the most important part. Every new light source changes luminaire design. LED sources are different from all previous light sources. Early sources simply needed a power source to operate. The LED is one part of a complex system that requires additional components to operate: driver, chip, optic, heatsink. Design stages has several stages: identification, selection, design, is system control are imported for the design parts. What are the characteristics of a well-designed LED fixtures? Thermal management for long lifetime, optical efficiency for volumetric lighting, quick disconnects of K components, and modular design. We need to know photometric data, first of all. Photometric data is a set of information related to the amount of light emitting from individual fixtures. Photometric data may include lamp power distribution, curve luminaire efficiency, utilization coefficients, physical dimensions, lamp or driver data, and efficiency. Optical system design approach, we know LM79 is a test method. Is created by the North American Association Lighting Engineers to measure the photometric data and electric properties of solid-state lighting, such as LEDs, gives guidelines for measurement in integrating sphere and goniophotometry. Sphere, we can measure luminance flux, luminance efficiency, and chromosity. Goniophotometry measures luminance intensity distribution and chromosity distribution. The result of this measurement is rich in the LDT file. This file helps us simulate the light distribution of the LED luminaire in the design program. Optical design programs and model creation. If we say luminaire efficiency describes the amount of light that is emits from the luminaire compared to the amount of light that is generated by the lamps. The most important factor for us to handle the luminaire output with the best result and correct curve of the light source is the lens. The material that will obtain the best optical distribution will maximize the efficiency of the luminaire. Programs used for compute software, ZMax, Optis, Light2, Trace Pro, Oslo, as Ravis, CPOs. Optomechanical design of Steam, SolidWorks, CATIA, AutoCAD. And for simulation, Dialux and Relux we can use. I would like to share some images thanks to these programs. And because of our company project, we exempt the surgical lamps. In this study, I discussed the difference values in the light degree outputs and cone diagrams of the product covered with white holder and transparent holder for a single lens because it is an important stage in the costing of the product. Because having white holder in the production raised the cost. I wanted to analyze this situation, convince our customer because trading is important. There has been enough reason for our customer. For the single lens produced from PMMA material, the effectiveness of the holder to the armature was discussed. Cree XTE series power LED was preferred as LED brand. Transparent holder, beam angle 8.6 degree, field angle 17.1 degree. White holder coated lens, can you see? Beam angles 8.5 degree and field angle 16.7 degree. But when the cone diagram is examined, it was measurement that the lux values of the white holder coated lens were better. It can also collect light originated from the internal reflections. So we at the end of this project, we preferred transparent holder, and LED lamps replace halogen lamps. Although the halogen lamps has a price advantage compared to LED lamp, it causes environmental pollution and it is not long lasting. And LED lamps are preferred more because they can perform shadow control clearly. Controllable, it is importance. Thank you for your attention. I would like to thank you, participants. If you have any questions, I would like to answer them.
Thank you very much, Esra Coach, for this informative talk given by one who take part both in the industry and the university sections of the lighting industry, I would say. As far as I can see, there is no question, but I'd like to ask one. Your point of view, I'd like to learn actually, because as I said, you have engagements both with the university and the industry. Considering the current studies of the LED luminaires and the current optical problems, would you share your opinion on the most important scientific problem of the optical problems within the optical problems that needs to be solved?
First of all, LED is
your voice is mute. Esra Coach? Okay, I think we have lost our connection. So I'd like to thank all our participants for joining us in this session and would like to invite you to Hall 1 at 2 p.m. So, bye.